Okay, so tonight we're going to be doing lessons 7 through 12 on these subjects. Some of them you may maybe become repetitive at some points, but that's okay because that's just how it's going to be. And lesson 11 and 12 are kind of newer for you guys that haven't been covered yet. So, but if at any point you have any questions during this, just let me know at the end and we'll go over them. Okay. So we're going to start with lesson 7, just common distributions. And if you remember, you learned about the normal distribution, which was bell-shaped, and it has a mean of 0 and a standard deviation of 1. It's also known as the z-distribution. And 100% of your observations will fall under this curve. So if you remember, like 95% confidence interval, things like that relate to the normal distribution. And if the sampling distribution is normal, we construct a normal distribution with a mean equal to the hypothesized parameter, which is just the number in the null hypothesis, and the standard deviation equals the standard error. And you can use these to find your p-value from your test statistic. So if you remember, the central limit theorem states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed. So as the sample size increases, the more normal your distribution will become. And then if you remember, a standardized score or a z-score is the distance between an individual score and the mean in standard deviation units. So we can use the normal distribution to conduct hypothesis tests. And throughout the review, you'll see this 5-step procedure a lot. Hopefully you've memorized it by now from your previous midterm, but this will become repetitive by the end. So first, you're going to check your assumptions and write your hypotheses. Then you're going to calculate your test statistic, then determine the p-value based on the test statistic. Then you'll make a decision whether to reject or fail to reject the null hypothesis, and then you're going to state a real-world conclusion, which just connects your decision back to the original problem or research question. So using the standard normal distribution method, the test statistic is the standardized value that is the boundary of the p-value. So as you see, the calculation for a z-score is just x minus x bar over the standard deviation. And then when you're conducting a hypothesis test, the sampling distribution is centered on the null parameter, and the standard deviation is known as the standard error. So your test statistic will then be, for a hypothesis test, your sample statistic minus your null parameter, which is just the number in the null hypothesis, over your standard error. So we're just going to walk through an example of this with the proportion of female students. So the research question asks if more than 50% of all campus STAT 200 students are female. So data were collected from a representative sample of 501 World Campus STAT 200 students. In that sample, 284 students were female and 217 were male. So we're just going to walk through the testing procedure of this. So the prompt is at the top if you want to refer to it again while we're going through it. So first, we're going to check our assumptions and write our hypotheses. So we conclude that our sample size is large enough, and we can write our null hypotheses, which are our null and alternative hypotheses. And our null is that p equals 0.50, and our alternative is p is greater than 0.50. So once we have our hypotheses, we're going to calculate our test statistic, which is just that p hat is 284, which is the number of female divided by the total number of students, and our p hat now is 0.567. And when we compare that to our hypothesized parameter of 0.50 and our standard error of 0.022, the standard error wasn't given. I got that from a randomization distribution, so don't worry if you don't know where that came from. So we calculate our test statistic to be 3.045, and we can put that on a distribution, on a normal distribution, to find our p-value. If we take a right-tailed test, we get a p-value of 0.00116, and that is sufficient that is less than our alpha, which is 0.05. So we can reject the null hypothesis, which states that our data is sufficient. And then we can state a real-world conclusion saying that there is evidence the proportion of all World Campus Stat 200 students who are female is greater than 0.50. Okay, so moving on to confidence intervals, we just did hypothesis tests, and now we're going to do confidence intervals. So you remember the general form of a confidence interval is your sample statistic plus or minus z star times your standard error. So you want to remember that your mean is your sample statistic here, and the standard deviation is the same thing as the standard error here. So the z-star multiplier, if you remember, can be found on the z distribution, which is the normal distribution as we talked about before. So yeah. So switching gears a little, but not really moving away from confidence intervals and hypothesis tests to binomial probabilities. If you remember, a binomial random variable is a specific type of discrete random variable that counts how often a particular event occurs in a fixed number of tries or trials. So for a variable to be considered a binomial random variable, it has to meet all of these three conditions. There have to be a fixed number of trials or a fixed sample size. The probability of success must be the same on each trial, so it creates sort of a level playing field there. And then just make sure that the trials are independent of one another, so one trial doesn't depend on the result of another trial. So an example I like to use when talking about binomial probabilities is the number of tails when you're flipping a coin 10 times. So if we go through the checklist here, we check to see if there are a number of fixed trials. So yes, we have a fixed sample size of 10. The probability of success is the same on each trial because if you think about it, there's a 50% chance a coin will be heads or tails each time you flip it. And the trials are independent of one another. So whether you flip heads on the previous try doesn't affect whether you'll flip heads or tails in the next try. So we can calculate the mean and standard deviation of binomial probabilities through these formulas. So for example, here we'll compute the mean of a binomial random variable and the standard deviation. So we're given an n of 5 and a p of 0.25. So to find our mean, we can just multiply the two together and we can get 1.25 as our mean. And then to find the standard deviation, we just plug those numbers into the standard deviation formula and we can get a standard deviation of 0.968. So there's not that much math to do here, but just make sure that you put the numbers in the right variable slots. So we just went through our first lesson. I'm going to end each lesson with a couple review questions before we move on to the next one. So this is the first review question for lesson 7. So for the SAT math scores, N of 500 and 100, let's apply the empirical rule to determine the SAT math scores to separate the middle 95% of scores. So you guys can take a moment. I'm going to pause and go over this in about a minute. And when you get your answer, you can enter it in the chat box. You can see what everyone got. Okay, so we're going to go over the answer to this. If you didn't quite get it yet, we're just going to go through it, and it shouldn't take you that long to do this, but maybe it'll clear things up if you're a little confused on how to go about it. So the answer is B here. So what we're going to do during this problem is you want to remember that the middle 95% of scores is, if you remember the empirical rule, within 2 standard deviations. So in that case, your z-score would be 2. You remember our z-score for 95% confidence intervals is typically 2. So we then would just plug it into our normal confidence interval formula. 500 is our mean. Add and subtract that to 2 times our standard error, which is 100. And we get a confidence interval ranging between 300 and 700 there. Okay, so our next question. Which of the following is not an example of a binomial random variable? Okay, so our answer here is B. So to go through the checklist of all the conditions that have to be met. So A and D are very similar. So they each have a 50-50 chance on getting heads or tails or true or false. They have independent trials, and they each have a fixed sample size. So A and D are out. And then when you go to C, since there are a fixed number of trials, so 500, it says unrelated people, so that means that they're independent of one another. And the probability of success is the same on each trial, because when you're comparing left and right hands, there's a 50% chance that someone will have be left-handed, or a 50% chance someone will be right-handed. So B is the answer here, because if we go through that, the conditions of a binomial random variable, so one, there are a fixed number of trials. Yes, there are 20 trials. That's good. The probability of success, however, is not the same on each trial, since keyword different kind of ticket. So with each lottery ticket, there's a different chance of winning, since they're all different. But if they were all the same kind of ticket, then that would count as a binomial random variable. Okay, so this is the last one for lesson 7, and then we're going to move on to lesson 8. Okay, yes, great job, you guys. The answer here is 7.5. So we're given a mean of, so to calculate our mean, so we're going to take our sample size times the p that we're given, which is 0.5. So 15 times 0.5 is 7.5. So there's not much explanation there, but great job. All right, so now moving on to lesson 8, which is inference for one sample. So these all kind of come together, but with all the formulas, and they're kind of repetitive, but just I have some charts at the end that kind of summarize them all up, so hopefully that'll simplify it a little. So we start with one sample proportion here, and if you remember the central limit theorem, which stated that as your sample size increases, the more normal your distribution will become. So it's kind of similar to the rule of sample proportions. So it really just compares your sample size to your proportion, and if it's sufficiently large, then your sampling distribution will be approximately normal. So of course your p is not known, but you approximate your p using p hat. You always want to estimate your parameter using your statistics. That's what we're given. So if all of our assumptions are met, our sampling distribution will have a standard error equal to the square root of p times 1 minus p over n. And that when our assumptions are met, we use the normal approximation method. And if our assumptions are not met, we will use the exact method. So we're going to start with confidence intervals for one sample proportion, and then, of course, do hypothesis tests after. So for normal approximation method confidence interval, we want to check that we have a sufficient number of successes and failures in each sample to make sure that our sample size is sufficiently large enough. Those are mostly our assumptions here, so we want to make sure that we have at least 10 successes and 10 failures, and that passes our assumptions, so we can use the normal approximation method. So once we pass our assumptions, we can use the normal approximation method confidence interval formula, which is in the orange box there, p hat plus or minus z star times our standard error. So remember that the value of the z-star depends on the level of confidence. So we talked about before that a 95% confidence interval, our z-star would be 1.96 or rounded up to 2. And then our standard error is computed using p hat as an estimate of p, which I already mentioned previously in the last slide. So sometimes you'll have to compute a necessary sample size. So it's kind of like, I think of it as like kind of working backwards. So we start with the confidence level and a margin of error that's given to us, and we have to determine a minimal sample size needed in order to produce those results. So instead of starting with the sample size and determining a margin of error, we start with a confidence level and margin of error to determine the sample size needed to produce those results. So here's the formula for finding a sample size for a population proportion. So we're going to use margin of error here and the estimated value of the proportion. And if you don't know the estimated value of the proportion, so if you're not given one, for example, you can use 0.50, because if you think about it, it provides the largest sample size calculation needed, and you would rather, you just want to make sure that you'll produce the results needed, even if your proportion isn't necessarily correct or what they were looking for. So next we're going to talk about one sample proportion of hypothesis testing. So this will have a similar layout to the 5-step procedure we talked about earlier. But a hypothesis test proportion is used when you have one sample with one categorical variable. And the hypothesized value of the population proportion is symbolized by PO, because you're using the value in the null hypothesis of HO. So again, you're going to check your assumptions. So you're going to make sure that there's at least 10 successes and 10 failures, and to make sure that the distribution is approximately normal. And And if it does not meet your assumptions, you'll have to use a binomial distribution, which we use Manytab for, we don't use by hand. Okay, so we're back to that 5-step procedure. So you're going to check your assumptions, write your hypotheses, make sure that there are at least 10 successes and 10 failures. And then you're going to calculate your test statistic using the formula on the right in the orange box. I'm going to spare you of not reading it out loud because it's kind of a mouthful. But once you get your test statistic, you're going to determine your p-value using the normal distribution. And then once you get your p-value, you'll make a decision. So if your p-value is less than or equal to alpha, you will reject the null hypothesis. And if your p-value is greater than alpha, you will fail to reject the null hypothesis. And then after that, you'll state a real-world conclusion to kind of put your decision into context of the problem. Okay, so we just did one sample proportion, and now we're going to do one sample mean. So remember the central limit theorem? Here, for one sample mean, a large sample size is considered one that has a sample size greater than or equal to 30. So those are our assumptions when we're using one sample mean. And we're going to be using the t-distribution instead of the z-distribution. And the only difference really between the two are the t-distribution varies depending on your sample size. You remember you have to input your degrees of freedom, which is based on your sample size. And with confidence intervals and hypothesis tests, you use the t-distribution when you're working with one mean only. Okay. So again, the t-distribution is determined by the degrees of freedom. And for one sample mean, your degrees of freedom is equal to your sample size minus 1. So you remember the general form of your confidence interval? It's your sample statistic plus or minus your margin of error, which is just your multiplier times your standard error. And then your confidence interval for a population mean is similar. It's x bar plus or minus your t star times your standard error here, which is just the standard deviation over the square root of the sample size. So again, we already discussed computing necessary sample size before with one sample proportion. And you can do the same thing here, except it's only different because the t-distribution is different for each degree of freedom, so there will be a different formula for computing a sample size for one sample mean. And then just remember to round up your answer for these because you want to make sure that you meet that minimum sample size requirement. But otherwise, the formula for estimating a population mean is as follows. You're going to use the z multiplier and estimate your population standard deviation and then your margin of error. So again, hypothesis testing for one sample mean is very similar to one sample proportion. It's pretty much just different in the first 3 steps, and the last 2 are pretty much the same. So your assumptions here are going to be that your sample size must be approximately large enough, which just means that it has to be greater than 30 here. And then you're going to calculate your test statistic using the general formula we've been using, and then determine your p-value. You'll use the t-distribution to find your p-value, and then once you get that, you'll decide whether to reject the null hypothesis or fail to reject the null hypothesis, and then you'll state a real-world conclusion. Okay, so paired means now. So paired means are also known as dependent samples. So just remember that they're not independent of one another, they're dependent on one another. So it can usually involve 2 things. So it can either involve taking 2 measurements on the same subject. So as an example, the effectiveness of a diet plan. So you weigh each participant before and after the diet and then compare the data. So for this case, you just see how much weight was lost to see how effective it was. Another example of paired data is taking one measurement on 2 related subjects, so studying twins, husband and wives, brothers and sisters, mothers and sons, so just related subjects. So when you're constructing confidence intervals or hypothesis tests here, you want to use the difference score for each individual or pair. So that's really the only difference between the other two. And then after that, the procedures are the same. So confidence intervals for two means here, the only real difference between them is that you use the difference between the two means here. So our x bar sub d, the subscript d stands for difference. And then we add and subtract that to t star times our standard error. So it's pretty much similar. Hypothesis testing can get a little more complicated with the number of formulas used to calculate the test statistic, but again, our assumptions, the only difference here is that the data must be paired, and then our sample size must be at least 30. And then once we pass those assumptions and write our hypotheses, you're going to have to calculate your test statistic based on your standard deviation and the difference in means. So once you calculate your test statistic, you'll determine your p-value. You'll use the t-distribution to find that. Make sure you input your degrees of freedom in there. And then you'll make a decision whether to reject or fail to reject the null hypothesis. And then you state a real-world conclusion. So yes, it's getting a little repetitive, but it's good to practice it. So this is everything that I basically just talked about summed up in one chart. So we talked about one sample proportion, one sample mean, and paired means, and we talked about each of their confidence intervals and hypothesis tests. So when you're looking at this, you can kind of see the patterns in each of them, and it makes it, I think, a little less overwhelming. Okay. So we just finished lesson 8, so we're gonna go on. I think there's only one review question for that lesson, but you guys can read through it. I'm just really asking you to calculate a test statistic here. And I gave you the data to the left, so you guys can go ahead and calculate that. Okay, great job, guys. So yes, 3.77 is our test statistic here. So it's kind of all written out there for you. Just plug the numbers into the formula. So you'll take your x bar and subtract the null, the mean, and the null parameter, and then and then you'll divide that by the standard deviation over the square root of the sample size, and then you'll get 3.771. So great job. Okay, so that was it for lesson 8. It was kind of a lot there, but we're moving on to lesson 9, which is inference for 2 samples, which is pretty much the same layout as lesson 8. So try to be efficient there. So two independent proportions. So two independent proportion tests are used to compare proportions in two unrelated groups. So you want to make sure that they're unrelated, and here you just use a difference in proportion test. So your assumptions, once you compare each, you just want to make sure that there's at least 10 successes and 10 failures in each group, not one or the other. You want to make sure that both meet your assumptions. And then you can say that your sampling distribution is approximately normal with that standard error formula there. I'm not going to bother reading it, but there you go. It's a square root of the proportions of each group. Okay, so we're going to go through confidence intervals and hypothesis tests for a difference in proportions. But first, with confidence intervals, if the assumptions are met, you can approximate the standard sampling distribution using a normal distribution. You want to make sure that you use a difference, that you find the difference for the mean. So you take p hat 1 minus p hat 2. And then for your standard error, it would just be the same formula from the last slide. So once you combine those two, you use the difference there and you add and subtract that to z star times your standard error. And that would become your margin of error, and then you would add and subtract that to the difference in the proportions. So with the hypothesis tests, you're going to be using the similar 5-step hypothesis testing procedure. So our assumptions here are just that there are at least 10 successes and 10 failures in each group. Make sure you check for each group and not just one or the other. So those are your assumptions. Then after that, you're going to write your null and alternative hypotheses. Then you're going to calculate your test statistic. So when you're calculating your test statistic, you want to use a pooled proportion, which you can calculate using each p hat and their sample size. And once you get the pooled proportion, you can calculate your standard error and your z. So that you're going to use all those to calculate your test statistic. And then once you get your test statistic, you're going to determine the p-value, and then you're going to decide between the null alternative hypotheses and then make a real-world conclusion. So the last 3 steps are pretty similar to all the hypothesis testing we've been doing. So really just make sure that you're aware of what's going on in the first 2 to 3 steps. Okay, so we just did 2 independent proportions. Now we're going to move on to 2 independent means. So with the means here, our assumptions are that each sample size is at least 30, and the sampling distribution can be approximated using the t-distribution. So once you get that, your confidence interval for 2 independent means is equal to the difference in the x-bars plus or minus t star times your standard error. And then your degrees of freedom here, you just want to make sure that you use the smallest n. So whichever group has a smaller sample size, you're going to use that to calculate your degrees of freedom and just subtract 1. So again, similar 5-step hypothesis testing procedure for normal approximation method. You're going to check your assumptions and write your hypotheses, calculate your test statistic, and determine the p-value using the t-distribution. Decide between the null and alternative hypotheses, and then state a real-world conclusion. Okay, so that's lesson 9 summed up in one chart, basically, with 2 independent proportions and 2 independent means and their respective confidence intervals and hypothesis tests. So again, you can kind of see the patterns between each of them. It makes it less overwhelming again. Okay, so this is the 5th review question, so you guys can take a moment. I'm just asking you to identify the hypotheses here, so as if you were writing the hypotheses. Okay, yes, great. B is our answer here because we're identifying proportions, and for our null hypothesis, it's just that there's no difference between between the groups of proportions. And then for our alternative hypothesis, we're just checking to make sure that there's a difference between the two. So we're not checking for greater or less than. Okay, so using the same data, calculate the sample proportion for a group over 40 that steal. So this is a pretty simple question. Some people think that it's like asking a really tricky one that uses a lot of that uses a specific formula, but it's pretty simple. Okay, you guys can. It should be relatively quick here. All right, great. Yes, D is our answer here. So I'm just asking for the sample proportion here. So to calculate the sample proportion, I asked for the group over 40 that steal. So you would want to look in the age group of those who are over 40 and then specify those that steal as the number in that category that I was looking for, and then divide that by the total number in the group over 40. So 76 over 192 equals 0.396 is our answer. So great job. And then this is our last review question for lesson 9. So you guys can go ahead, take a look, and just compute a 90% confidence interval using the data. Sorry, I kind of gave away the answer for that one a little in the beginning, but once we plug in all of our numbers, we get a confidence interval ranging from 5.29 to 8.99. So you'll really just want to plug in each group's mean in the beginning, and then I give you the t-star of 1.648 in the problem. And then in your standard error, you just plug in each group's standard deviation in the numerator and then their sample size in the denominator. All right, so we're on to lesson 10, which is one-way ANOVA. So this is one of the last subjects you guys had on your previous midterm. So you guys talked about the F distribution, which you compute F test statistics to determine a p-value for one-way ANOVA. So when you're using the F distribution, you have 2 degrees of freedom, when on the T distribution you have only 1 degree of freedom. So the F distribution has a between groups and within groups degrees of freedom. So the between groups you'll see sometimes maybe called as the numerator. It's the degrees of it's a degrees of freedom equal to k minus 1. So k stands for your number of groups. So it's just your number of groups minus 1. And then the other degrees of freedom, which is called within groups, is sometimes called the denominator. That's just n minus k. So it's your sample size minus the total number of groups. So here with hypothesis testing, remember you're going to check your assumptions and write your hypotheses. The assumptions for one-way ANOVA are, there's a couple more assumptions than usual. You want to make sure that your samples are independent. Then you want to check that your response variable is normally distributed, or that all your sample sizes are at least 30. So you're just making sure that it's sufficiently sized. And then your third assumption is that the population variances are equal across responses for the group levels. So you're just checking that the population variances are equal. So it's just really comparing the standard deviations to one another. And when you're writing your hypotheses for one-way ANOVA, you're going to, for the null hypothesis, you're going to make each group equal to each other. And then in your alternative, they will not all be equal to each other. So it really just depends on the problem that you're given there. But you just want to make sure that not all of them are equal in the alternative hypothesis. And once you get your hypotheses, you're going to calculate your test statistic. We don't do this by hand. You can, you guys have probably just used like Minitab to do this. It'll give you the 3 different degrees of freedom, and 2 of them you're going to need to look up the F values. So remember, between within the numerator and denominator, you guys can look up your F value, and then you can determine your p-value using the F distribution. And then you're going to decide whether to fail or reject fail to reject your null hypothesis, and then connect back to the original problem when you state a real-world conclusion. So it's pretty much similar, but there's a few things different in the first couple steps. Okay. So that went by pretty quick. We're just going to go into our first review question here. So find the numerator and denominator degrees of freedom for the F distribution. Okay, so this one is relatively quick. So our answer here is 2 and 242. So in the table we're given the between degrees of freedom and the within degrees of freedom. So the between is the numerator and the within is the denominator. So it's just 2 and 242. Okay, so if our numerator degrees of freedom for the F distribution is 4, then what is K? Okay, so our answer here is A. So if you remember, K is our number of groups, and our degrees of freedom we calculate as K minus 1. So if our degrees of freedom is 4, then 5 minus 1 equals 4, so our K must be 4. So good job on that. All right, so now we're moving into the newer stuff. So lesson 11 and lesson 12, and then we're done. So chi-square tests first. So this stuff should be relatively new. So goodness of fit test, if you remember, it can be conducted when there's one categorical variable with more than 2 levels. So if the expected counts are all at least 5, then you're going to use a chi-square test. If any expected count is not at least 5, then you use a randomization test. So back to the goodness of fit test. So you compare observed counts to expected counts. The observed counts are the number of cases in the sample in each group, and the expected counts are computed given that the null hypothesis is true. So when you're computing expected counts, you assume that the null hypothesis is true. So yeah, so when you're calculating your expected counts, you just take the sample size times your hypothesized proportion for the particular group you're calculating. And then once you get those, you will calculate your chi-square test statistic, which compares each cell's observed and expected counts. So chi-square distribution, we have T distribution, F distribution, Z distribution. Now we have chi-square distribution. So again, this varies depending on your degrees of freedom. For chi-square test, your degrees of freedom will just be your number of groups minus 1. So to find the p-value, you're going to find the area under the chi-square distribution to the right of the test statistic. Remember, when you're finding your p-value on a chi-square distribution, it'll always be right-tailed test. So again, we have a 5-step hypothesis testing procedure. You're going to check your assumptions and write your hypotheses. So for chi-square tests, it's recommended to write them first. So the null hypothesis will contain your equalities, and the alternative will have that at least one of them is not as it is specified in the null hypothesis. And really your only assumptions here are that all expected counts must be at least 5. And you can calculate those by multiplying the sample size times the proportion. And once you write your hypotheses, you can compute your test statistic, which just, again, compares your expected counts and your observed counts. And then you just add them all together for each cell. And then you will determine your p-value. So you will construct your chi-square distribution with your degrees of freedom, which is equal to the number of groups minus 1. And then you will take a right-tailed test under that distribution to calculate to find your p-value. And then you make a decision whether you reject the null or fail to reject the null. And then you're going just remember to address the original question based on your decision. So, of course, that's always the last step, but just don't forget. Okay, so a chi-square test of independence. you use this between two categorical variables. So what a chi-square test of independence does is it computes expected values for cells in a two-way contingency table under the assumption that the two variables are independent. So again, here you're going to use a 5-step hypothesis testing procedure. So it's getting a little repetitive, but you guys should definitely have it down by now. So step 1, you're going to check your assumptions and write your hypotheses. So they're similar to the ones that we just had before. So your expected counts must be at least 5. So your sample, you also want to make sure that it's randomly drawn from the population. And then when you write your hypotheses, your null hypothesis will just be that there's not a relationship between the two variables. They are independent. And then your alternative hypothesis will be that there is a relationship between the two variables and they're dependent on one another. So once you write those hypotheses, you're going to compute a test statistic. So you'll compute your test statistic based on each expected cell value. So you can use those formulas there in the bottom. All right. And then you can determine your p-value in step 3. So you're going to construct your chi-square distribution. Different here, your degrees of freedom are different because you're using a contingency table. So the way you calculate your degrees of freedom is you take the number of rows minus 1 and then multiply that by the number of columns minus 1. And then you'll take a right-tail test again for the test statistic. And then just decide whether to reject or fail to reject the null hypothesis, and then state a real-world conclusion. All right, so relative risk. This is pretty new. So if you remember risk, which we worked on earlier in the semester, you definitely need to know that because you'll be going back to midterm 1. But risk is used to describe the probability of an event occurring. So you calculate risk by the number with an outcome over the total number. So for example, for flu, so 45 out of 100 children get the flu each year. So the risk is 45 over 100 or 45%. So relative risk compares the risk of a particular outcome in different groups. So you'll compare the risk in group 1 and the risk in group 2. So with relative risk, you're comparing risk. You're not calculating risk. You're just comparing two risks in each group. So again, if we use the flu, suppose that the risk of a child getting the flu this year is 0.45 and the risk of an adult getting the flu is 0.10. What is the relative risk of children compared to adults? So we would compare the risk in group 1, which is 0.45, over the risk in group 2, which is 0.10. And we would conclude that children are 4.5 times more likely to get, more likely than adults to get the flu. Okay, so here's review question number 10. So when randomly selecting a card from a deck with replacement, are we equally likely to select a heart, diamond, spade, and club? I randomly selected a card from a standard deck 60 times with replacement. Calculate the expected count. Okay, great job. So yes, B is our answer here. So we first want to calculate our proportion. So we have 4 options here: heart, diamond, spade, and club. So there's a 25% chance that we would select one of those. So 0.25 is our proportion here. And then we just multiply that by our sample size of 60 and we get 15. So great job. Okay, so our next review question is to calculate the degrees of freedom for this chi-square test of independence using the chart on the right. So this should be pretty quick. All right, great job, guys. Yes, it is 1. So if you didn't get that, we just do the number of rows minus 1 times the number of columns minus 1. Here it works out that there are 2 columns and 2 rows each, so we just end up multiplying 1 times 1, and our answer is 1. So yes, great job. All right, so here's our last review question for lesson 11. So suppose 4% of teenage girls have asthma compared to 9% of teenage boys with asthma. Using the males as group 1, what is the relative risk for, well, it should say boys compared to girls, but what is the relative risk for boys compared to girls? All right, great job, you guys. So for relative risk here, we're comparing boys to girls, so 9% to 4%. And then we just put 9 as our numerator and 4 as our denominator, and we get 2.25. So we can say that the risk of asthma is 2.25 times as great for teenage boys as it is for teenage girls. So great job on that one. All right, so we're in our last lesson here. Correlation and simple linear regression. This is the most recent stuff you guys have been working on. So correlation, remember, Pearson's R is a measure of correlation between 2 quantitative variables. So when we're talking about a sample, we use the symbol R. And then when we're talking about a population, we use the symbol rho, which kind of looks like a P, but it's not really. It's not a P, but it kind of looks like a P. But that's called rho. And there's just like 5 properties of Pearson's R. So R will range from -1 to 1. So for a positive association, R has to be greater than 0. And for negative association, R is less than 0. And then if there's no relationship between 2 variables, R will be equal to 0. So the closer R is to 0, the weaker the relationship. And the closer to +1 or -1, the stronger the relationship. So really the sign of the correlation, whether it's positive or negative, really only provides direction. It doesn't indicate how strong or weak a relationship is, because it can be -1 but still be very strong. So sign only provides direction, whether it's positive or negative. And correlation is unit free, so you can compare yards to inches and it will still have the same correlation, so you don't have to worry about units with correlation. And the correlation between y and x is equal to the correlation between x and y. So when you're comparing the 2 quantitative variables, it really doesn't matter which one is x and which one is y. So these are just some correlation coefficients to just to keep in mind how you would just the strength of a relationship. So it ranges from very weak to very strong. So obviously 0 would be a very weak relationship, and then 1 is very strong, and then in the middle would be moderate. So that's just kind of gives you the idea of how you define the relationship. But So again, with the hypothesis testing for the correlation, so first you want to check your assumptions and write your hypotheses. So our assumptions here are that both variables are quantitative and, and the relationship between x and y must be linear. And then when we write our hypotheses, you'll just want to make sure you write in terms of rho, because in terms of the population, at least so for here, you'd be using rho. So don't forget that, definitely. So you would do rho is equal to 0 for your null hypothesis, and then your alternative would be that rho is either greater than, less than, or not equal to 0. So it really depends on what the scenario is. So after you write your hypotheses, you're going to calculate your test statistic, determine your p-value, decide whether to reject the null or fail to reject the null, and state a real-world conclusion. So you guys should be experts at this by now, definitely. Okay, so simple linear regression. So simple linear regression uses one or more explanatory variables. So remember, your explanatory variable is your x variable or the independent variable to predict a response variable, which is y, or the dependent variable. So it's kind of similar, if you remember, from like algebra, y equals mx plus b. It's very, very similar to this. Has a similar formula. So your predicted value of y is equal to your y-intercept plus your slope times your x. So your slope is a measure of how steep your line is. So rise over run. It's also your change in y over your change in x. So a positive slope indicates a line moving from bottom left to top right. And then a negative slope is a line moving from top left to bottom right. So you can kind of see on the graphics to the right there how a slope is positive or negatively defined. And then your y-intercept is just the predicted value of y when x equals 0. So if you were to plug in 0 to x, your y-intercept is what you would get for y if you plugged in 0 to x. Okay, so there are some assumptions of a simple linear regression. So the first one is linearity. So the relationship between x and y must be linear. Independence of error, there you have to make sure there's no relationship between the residuals and the y variable. You want to make sure that there's normality of errors, so the residuals must be approximately normally distributed. And then finally, equal variances, so the variance of residuals is the same for all values of x. Okay, so confidence interval for a slope. So very similar to our general confidence interval formula. You'll take your sample slope, add and subtract that to your t-star. So here with the t-star, you'll be using a value from the t-distribution, and your degrees of freedom here will be your sample size minus 2. And then you're just going to multiply that by your standard error of your sample slope. Okay, so your coefficient of determination is also called r squared. So it's really just the amount of variation in the response variable that can be explained by your explanatory variable. So you calculate this by, it's called r squared, but you literally square r, which is how you find your coefficient of determination. So it's pretty simple to remember there. Okay, so you guys remember talking about outliers earlier in the course, but most of the times you think of an outlier as decreasing the value of a correlation and like weakening the relationship between two variables. You kind of think of it as like it's in the way of the data and it kind of ruins it. But sometimes an outlier can increase the correlation value and make it look like there's a relationship when there really isn't a relationship. So we call that an influential outlier. So you see in the two figures below, figure 1 has the influential outlier, which is circled there, and figure 2 does not have it. So you see that the steepness of the line is very different in each. So the influential outlier really has an impact on the slope and just the correlation between the two variables. So it's just something to pay attention to. And then another thing to look out for is extrapolation. So extrapolation is defined as when you use a regression equation to estimate the response of a data point when the value falls outside the range of the explanatory variables used to create the regression. So an example that I like to use for this is if you're trying to estimate the height of a child, but you use the data for heights of adults. So yes, you could use that to estimate the height of a child, but it would not make sense because you're not used to working with that small of numbers if you're assuming that the child is much shorter than the adults. So in order to get a good estimate there of the child's height, you would have to collect data on heights of children and then use that to estimate. So it's really just using estimating data that falls into the range of other explanatory variables of that kind. Okay, so we're going into our last review questions. So I give you the equation there. So really just when x equals 0, what is the predicted value of y? So it's really just finding the y-intercept here. All right, yes, so A is our answer. So really just plugging in 0 for x, you would get 3.5 as your answer. So there's not much explanation there. Okay, so the correlation between quiz averages and final exam scores was R equals 0.60863. Calculate the coefficient of determination, or R squared. All right, great job, you guys. So yes, 0.370 is our answer. Oops, sorry. So really here, you're just taking R and multiplying it by itself. So 0.60863 times itself, and you'll get 0.3704. So great job on that. So I think this is our last review question here. So calculate the confidence interval for a slope using the values given. So I gave you the slope, the t-star, and the standard error there. All right, so here you're just going to find your margin of error, which is just the t-star times the standard error, which comes out to be 0.2807. And then you're going to add and subtract that to the slope of 0.8034. And then once you do that, you get a confidence interval of 0.523 to 1.084. All right, so that is all. Thank you guys so much for coming. Have good luck on your final. I hope you all do a great job. I know you will. Thank you for coming. Yes, this will be recorded. I'm recording it now. This will be posted on YouTube